All right, reminders. Your programming test result is going to be, is going to be released definitely this week. I'll try to get it done early Friday the latest. If I can get it earlier, I'll definitely give you the feedback earlier. So you can take a look and then feel free to reach out to me by e-class. Actually, we have a regrading procedure for you, but I'll get to you about the details. And don't forget, we also got a makeup lecture for you, and that will be important for your written test number 2. Let's take a quick look on where we are right now. If you go to the semester calendar, okay, you can see that we are now right here on the 13th, right? Lecture 17. And we're going to finish today's lecture. I think most likely your written test 2 will cover only until over here. There might be some very minor details I may have to carry on to Wednesday, but if that's the case, I'll let you know. But you can definitely get started. I will release the study guide for you to you about written test number 2, hopefully by the end of today, so you will know exactly where the coverage is. For the practice question, I'll definitely try to make it available to you before Wednesday's class. So just get started preparing for that. And your written test number 2 will be next Monday, this time in the Williams Small Center. No surprise. You just have to make sure your PPY login works, dual mobile, and also your EECS login, right, like last time. Just make sure, and then you should be all set. Your assignment number 3 will also be released this week, hopefully very shortly after Wednesday's class. And then you can get busy with it, and that will help you a lot on programming test number 2. All right, so that'll be the plan. All right, so last time we started talking about a general tree, ADT, right? So every time you talk about some ADT, you have to know what kind of terminology, what kind of operation we can perform on the trees. We haven't talked about operations so much just yet, but we will as we move on with the lecture. For the first bit of today, let's focus a little bit more on terminology, just to give you more ideas. So what have we covered last time? Let's do a very quick recap. Right, we talk about what the root is. There's only a single and unique root. And given, for example, one pair of nodes, one is called a parent, the other one is called a child. And sometimes you may have one pair of nodes. You cannot say Chris is a parent of Shirley because it has to be immediately above. Right? Just watch out for the definition. And we talk about ancestor and descendants. That's the more general way to talk about between nodes. For example, I might say Elsa is David is the ancestor for every node, including itself on the tree. And similarly, for Vanessa, she is one of the descendants of David. Right? So you want to review the definition for ancestor and descendant. And we'll cover a little bit more today about these two. And siblings. All the nodes that share the same parents are called siblings. Okay? And we talk about subtree, right? And also make sure you know how to calculate the number of subtrees given the tree. And also I might say, I want to get all the subtrees of a particular size. In that case, you should also calculate for me. Right? This might be appearing on your written test number 2 next week. And the final bits we talked about last time, let me start from here. Just talk about again. The notion about external nodes versus internal nodes are so important. Okay? The definition is very easy. Any nodes that has no children are called the external nodes. For example, you can see Shirley, Vanessa, Peter, Anna, and Ernesto. They have no children. Or alternatively, their descendants consist of just themselves. For example, what would be the descendants for Shirley? Not empty, herself, right? What about internal nodes? Anything that's not external should be internal. They're like a mutually exclusive concept. Internal nodes simply means you got at least one child, at least one, or 2 or more descendants, right? Think about that definition there. For example, David over here, he definitely got more than himself being the descendants, but also all the other descendants. So David is internal. What about Elsa? Elsa, you can see, in addition to herself being her own descendants, also she got 1, 2, 3 children, right? So she's also internal.
The leaves, they're the external nodes, right?
Yes, correct. So sometimes people like to talk about external nodes being leaves as well of the tree. Think about the leaves are simply just around the very far edge, the very far boundary of the tree. Yes. All right. Guys, any questions so far about that definition? We have to introduce a little bit more, and then we have to talk about how we can implement the tree using Java, which is not too bad. I think you guys are ready for that. Okay, so let's now talk about the next set of terminology. Okay, we want to talk about the notion about edge, path, depth, and also heights. So these are the four we want to talk about first. All right, let me go over definition one by one, and then I'll visualize what they really mean. Okay, if you go back to the slides, this is where we were last time. Let's start with the edge. An edge is simply a pair of nodes, not arbitrary pair. The pair must consist of parents and child. It would be called an edge. All right, so for example, let's say this one over here is an edge. This one here is an edge because apparently David is the parents and Ernesto is the child. Right? It's an edge. On the other hand, is there any edge between Elsa and David? Not really, because David is not the immediate parents of Elsa, so there's no edge. Right? Simple definition. What about path? I mentioned something called ancestor path last time. Basically, a path in general would just be a sequence of edges you can form together. Right? So let's look at the definition. So a sequence of nodes which can form two consecutive nodes from an edge. Okay, let's take a look. A path of tree. Let's take a look at one path. You can see, let's say, starting from Vanessa. Okay, starting from here. This is one edge to go from Vanessa to her parents, Elsa, and go from Elsa to her parents, Chris, and go from Chris to his parents, David. So 1, 2, and 3. 3 edges. It forms a path. We wouldn't typically say an edge itself is a path. It might occur sometimes because the path can be as short as just one single edge. It's possible, but not very often. Typically, the base cases for you to handle. Okay? Let me write it down over here. So this will be a path. In general, it could be as short as just one single edge. It's possible, but normally it's not very useful. As short as one single edge. And here I talk about as short. Okay? Let me give you another property. What about as long as what?
As long as the root to the
Yeah, let me give you the answer first, and then we'll go over that definition. Okay, as long as the height of the tree. And of course, I haven't gone over with you guys what height is. We'll do that. As the height of the tree. Right? Basically, we're talking about the minimum and also the maximum. Right? Could be a single edge, or it could be the heights of the tree. But we'll get there. But just make sure you understand the property first. So the edge and the path, they are pretty straightforward. And what I want to do now is to define depth and also height. To do that, I would suggest I will make a clean picture for you, so you wouldn't get confused. And it's better to actually talk about both at the same time. Okay. Right, let's see the definition. So I want to talk about, number one, I want to talk about depth. Sorry. Sometimes I simply forgot how to spell that. Depth of a node versus heights of a tree. And here, I want to be more precise. It could be a subtree. For example, I don't necessarily just ask you about the height of this particular tree. I can ask you what's the height of this particular subtree. That's also possible. But whenever I talk about the depth of a node, it can be some arbitrary node. Can be the root, can be some external nodes, can be some internal nodes. All right, let's now see the definition, and then we'll visualize. We'll annotate the diagram a little bit to help you understand. But let's take a look. Okay, there we go. Okay, this is a simple definition for if I'm given a node n. number of edges from the node all the way to the root. That's the definition. You can say from the root to that particular node, or from the node all the way to the root. Either way, they will give you the same answer. Okay, so how do we calculate that? Let's just see some example here, and then we'll see something very useful. Let's now start with, let's say, Vanessa. Okay, what will be the depth? Usually we just say D. By definition, it should be about how many edges it will take Vanessa to traverse all the way to the root. 1, 2, and 3. By definition, it's just 3. Okay? 3 here, there are 2 different ways you can interpret this. Either you can say number of edges to the root. Can you guys see another way to interpret this? And I'll give you a hint. Ancestors. If I tell you how many ancestors there are for this particular node, can you calculate accordingly the depth of that node? Variance. -1, exactly. Don't forget, it also includes the node itself, right? Good. So for example, you can see Vanessa here. How many ancestors do we have? Herself, 2, 3, and 4. And 4 minus 1 will give you exactly 3 edges, right? That's another way to interpret that. I'll write it down, and I'll take questions. Number of ancestors -1. Both of them are equivalent expression, but I would suggest you know both interpretations. Sometimes one might be a little bit useful than the other. Okay? Question somewhere. Yes, go.
For example, if you look at Anna, she has like 2 ancestors. But like.
Okay, first of all, Anna does not have 2 ancestors. Oh, okay, yeah, sorry. Anna has only one, yeah, you're right, 2 ancestors. Sorry, go ahead.
So yeah, but looking at that, you calculate the depth of like a single node. Like when you, can you like,
Okay.
all these are lost.
Yeah, you're more a little bit thinking ahead, but I can give you a look ahead. Let's say, for example, if I want to calculate the depth of Anna, as I said before, guys, if you want to do some computation on the tree, recursion is a very natural way of to think of it. Okay, let's do some very hand waving before we get to the code. How do I calculate Anna's depth? It should be this edge itself is 1, right? 1 edge, plus whatever depth it is for Anna's parents. I'm talking about 2 things. One here is something I know right away. And the depth of Anna's parents in general could be something that's subject to further recursive call. So that's something I need to specify in my Java code. And I will show you exactly how this will look like in Java, and then we'll trace it, and then hopefully that will help. For now, it's just hand waving a little bit. Okay? All right, let's do a little bit more. Let's just do one more. What about, oh, since we talk about Anna, what about Anna here? And here, I can just tell you that D will just be equal to 2. Right? Because we got 1 and 2 edges to the root. And the notion about depth. Yes, go ahead, please. Okay, yeah, so usually the ancestor path, well, I wouldn't worry too much about the shortest path over here, actually. So in some way, you're right. If I want to go from a node to the root, actually, there's only one way for you to go there, which is by keep getting the parents and then until you get to the root. There's only one way. But at the same time, of course, it will be the shortest path. But usually, we only talk about the shortest path when we talk about the graph data structure, but not here. Yeah, so you don't need to overthink. Okay. All right, so why is the notion about depth so important? Okay, we can use the notion about depth to really divide the trees in the different hierarchy at different levels. Okay, I'll write it down and then I'll show you what I mean. So we're going to use the depth to divide the tree nodes into different levels. Into levels. All right, what do I mean? Okay, let's see. You may have seen this maybe very gently when I talk about linear versus nonlinear structure earlier. Okay, so this is one division here. This is one division over here. This is one division over here. All right, for the first division, it contains all the nodes with depth just 0. That one makes sense because for this node here, it's simply the root. By definition, it takes no edge for David it's himself to the root, which is himself, right? 0. Okay? And then the next level will be all the nodes with depth just 1. You can see for Ernesto to go to David, just one edge. To go here, also one edge, right? D equals 1. And then the next level will be all the nodes with depth 2. Final level will be depth equals 3. And in the case where your trees happen to be a binary tree, you will have some very nice mathematical property. We may not be able to get there today, but hopefully on Wednesday for sure. All right, guys, that's about depth. Any question before I talk about the heights of a tree, which is highly related? Okay, good. Let's go over definition before we have to annotate the tree. You will see a little bit some different example on the slides. You can definitely take advantage of that. All right, what is the height of a tree? Again, the tree doesn't need to be the entire tree. It can be any of the subtree. Okay, if I give you some subtree, its height by definition is the maximum depth among all its nodes. So that kind of tell you some kind of concept about looping, right? Let's say I'm now the root of some tree. Underneath me, I got many descendants there. How do I know how high I am? I have to somehow recursively figure out the heights of all my descendants and then choose the maximum. That's kind of the idea, right? But let's see. Since we have already annotated the tree in a very proper way, we got all the depth for all the nodes already. So let's now see by definition, how do we calculate? Let's now try something simple. Okay, I'll tell you the simplest one. This is a subtree, right? So the way to ask the question is, what is the height of the subtree rooted at Shirley? Height of subtree rooted at Shirley. All right? Now, do you guys know the answer? Let me give you the definition again, and then you should be able to tell me quite easily, right? Maximum depth among all the nodes. Let me give you one possible answer, okay? I will argue that maybe it should be 3 because this node here has a depth 1, 2, and 3. So its height should be 3. Do you think this makes sense? If it doesn't make sense, Farrads, what do you think should be the right answer? Yes, exactly. That's very good. Good. So guys, what I just said to you was really deliberately trying to mislead you, right? Be careful. Okay, let me say it again. What I said earlier was also some common mistake, which I saw some student did. So I want to make sure you don't make the same mistake. The way I said it would be, because Shirley has a depth 1, 2, and 3. But the problem is, we are now talking about the height of this particular subtree. We should really restrict our scope only to this subtree. If I go to another tree, it's completely not relevant. Okay? So now, like Farrad said, if we got this subtree over here, the only node we have is over here, surely the root. What's the depth by definition? 0. Yes, thank you, 0. So that means it's going to be 0. Right? I'm being very careful about clarifying because once we get to the more advanced mathematical property, you got to make sure you know where you are. Okay, so 0. I can explain one more time. Okay, given this particular subtree, which contains a single node, what is the height of the tree? By definition, you're going to figure out the depth of all the nodes in this particular subtree. But the only node you have is the root itself. And the root, by definition, has depth just 0. So that's why the height should be 0. Okay? All right, let's try something slightly more complicated. Slightly. Okay? How about this one here? Okay, not too bad. So I'll put a question here. What is the height of the subtree rooted at alpha? Should be 1. Why is that 1? Yes, yes. So another way you can also try to maybe annotate yourself. Of course, you got to make sure you don't get yourself confused. As far as this purple subtree is concerned, you can divide them into 2 levels. Level number 1, we still got depth equals 0. Level number 2, we got depth equal to 1. So the maximum depth will be just 1. Right? So the height will just be 1. Okay, over here. All right, final question. Final question. Let's now look at the absolute root. What about the heights of the tree rooted at David? What would that be? What's the maximum depth about all the nodes? 3, okay, good. But you can actually definitely refer to it like what we did earlier, which is over here, right? You can see here we got 0, 1, 2, 3. Yeah, maximum depth for sure. 3. All right, hopefully you got the definition. And what you really want to think about meantime, before I show you the Java version, in order to calculate the depth, let's say I'm given this node. What would be, let me say this. If I have Vanessa over here, if I want to calculate her depth in the tree, one edge plus recursively the depth of her parents, right? Very informally. What about if I'm given, let's say, the root of some tree? I want to know its heights. This one here also is not too bad, okay? Basically, you want to somehow recursively calculate the heights of each child. Choose the maximum. Once you got its height, you have to add 1 to it because there's also one edge connecting the nodes. Let me say it again, and we're going to see the code. Given some arbitrary node being the root of some subtree, what would be its heights? Number 1, you have to write a loop to go over each child one by one. For each child, you have to recursively calculate the heights and calculate the heights. Height number 2, height number 1. Find the maximum. For example, let's say it's this one here. Once you find out the maximum, it's not the answer just yet. You have to add 1 to it to really address this particular edge. All right, that's the idea. And I'm going to show you the Java code very soon. That'll be the more like a hello world example to tree manipulation. All right, I believe that's everything I wanted to say about these 2 notions. All right, guys, any question, please? Okay, hopefully it's not too bad. All right, so this, I think just some more example. That's how we divide the trees into different levels. And for these, you can just take a look. A little bit different example from what I showed on the iPad, but you can just get more exposure to it. General tree definition. Okay, let's now do a little bit recap about what we learned about what a tree is. Okay, the tree itself really has a recursive definition. Let's now make sure that's clear before we show you the Java code. The simplest case is when you actually got an empty tree. I would say case 0 when you actually got empty tree. Usually when you get an empty tree, that's also the base case, one of the base cases. And when you have this, that means the root is going to be one of the attributes for the tree. The root will just be pointing to just null. And of course, the size of the tree is simply equal to 0. And sometimes people like to use the empty set symbol to represent a tree, because a tree is like a set of nodes. Okay, either way. All right, that's case number 0. Okay, let's talk about case number 1. Let's say if you have a single node in the tree, how do we represent that? And the way we write a Java code, define the Java classes, is really try to mimic this way of understanding. Okay, case number 1, let's say a singleton tree. Like a singleton set, only one node, a singleton tree. Okay, it will look something like this. So the root is going to point to some node. Okay, apparently it is not null, just that. And there would be a attributes over here called children. Okay, children. And children here, it depends on what your implementation is. You can say it is children is simply just null, no children, or you can say it is simply just pointing to some empty array. So either way, that one is kind of up to your implementation. All right. And of course, in this case, size would just be equal to 1. So far, these are the two very common base cases when you want to work on recursion on the tree. Either when it's empty, or it's only the root. What about recursive cases? That means you got more than one nodes in the tree. Let's try to visualize that a little bit, and then we'll see how to manipulate it once we see the example in Java. Okay, final case. So case number 2, when you got more than one nodes in the tree. In general, you want to think about the root over here is pointing to some node over here. And the node itself has some children attributes. And the children over here, in general, is going to be a linear structure. When I say linear structure, that means it's like a sequence. And in this case, you do have a choice. Either you want to implement the children attribute using an array, which is what I'm going to show you in the lecture example. Or if you want to use a simply linked list, which is, I believe, what you will do in the assignments. So you got both. What about the programming test? Whatever you do for the assignments, your programming test will just be consistent. Okay, but you can definitely see both in the course. Okay, but for now, let me draw just an array. So we got index 0, index 1, index 2, and etc. Since we are talking about general trees, so the number of children you have does not need to be 2, in which case it will be a binary tree. But for now, we don't need to worry. Okay, so think about, so this one here is going to be just another tree. Okay. Okay, so this is what you can think about as the subtree rooted at the first child with the child index 0. And of course, there might be some nodes over here. And I would say this definition here about a tree will go back to case 0, case 1, or this. Because the subtree over here can either be simply empty, in which case we simply don't have any child, right? Or it could be just one single node, in which case there's only one node in this subtree. Or it could be arbitrarily large. I'll do a recap in a moment, but so this will be something similar, right? So this will be just another subtree rooted at the second child, right? Second child with index 1. Okay, let me recap, and then we can move on. When you talk about trees in general, it's really a recursive definition. The two base cases are when the tree has no node or the root is simply empty. And the base case number 1 will be when you have only the root. Recursive case tells you you at least have the root. And then from then on, you have as many subtrees as you like for rooted at each child of the root. And then how complicated each subtree should be Again, it's up to the definition about case 0, case 1, and case 2, right? Just go on and on and on, the pattern. Okay? So it's really important to really think a little bit more recursively. Okay? All right, guys, any question about this kind of visual sketch about the idea? You mean this? Here, just easier to see from the diagram, so I'm only mentioning about the size. I will talk more about the depth once we get to the binary tree a little bit later.
Is it just the number of all the nodes in the tree, or is it like the same as depth?
You mean all the nodes in this tree have the same heights? Is that what you're saying?
Well, just like the terminology size, is it referring to either depth or height, or is it like a different?
No, the size here is very generic. It's simply about how many nodes are there in the tree. Yeah, which I didn't even bother to mention because that one's so straightforward. Right? Okay. All right, a little bit more terminology, and then I will try to get just before we have to talk about binary tree, and then we can take a short break. Okay. Okay, let me see how much time. Okay. Okay, so that's the slides we just went over. Okay. Yeah, so this is saying, so there's always a single unique path from the root to any particular node. For example, let's say this is the root over here. In order for me to get to, for example, this node, there's only a single path. And let me just give you a little bit more complicated example. Let's say this is a root. This is the root. How many paths there are to get to Vanessa? Only one. Here, here, and here. If you have more than one way, for example, from here and then to here, then this is not a tree anymore. Okay, it's important. Okay. Yep, so just give you a more legal versus illegal organization of the tree, right? So this slide here is also rather straightforward. That's a property about a tree. Okay, let's talk about the notion between order versus unordered tree. So a tree is ordered if there is a meaningful linear order, which means there's a notion about which one should come first, which one should come after, okay, among the children of each internal. Okay, let's give you just one example. All right, so this is more like a structure of a book. You can see here the top level may be the title of the book. You can see these are the children at the first level, right? So let's apply what we learned earlier. You can think about these are the children with depth 1. And there is some linear order among them. So that means preface should really come first, and then part A, and then part B, and then references. Right? That makes sense. So the order does matter. There is a linear order. And again, whenever we talk about the order is linear, that means there's some notion about predecessor and successor. Amount, children at the same level. Okay, and I can talk about the other one right away. So this tree here is so-called the unordered trees. But this could be, I can tell you that this may not be the perfect example. But this is more like, if you want to try, if you log into your account at the web server, right? You can go into some, maybe CD, to some directory. And you can try tree dot. Okay, this one here is actually going to give you the tree structure of your directory. I'm not too sure if you used it before. It's quite a nice command you can try. You can just try the remote lab, and then you will see. Right, so one possible example would be, you can see among this directory here and this directory here, we don't really say which directory should really come first. This could be a little bit debatable, right? Sometimes this may not matter, but sometimes you might say maybe one folder has been named in a way, maybe by its chronological order, so that one should really come first. So I would say, just understand the idea. If the nodes at the same level should have no order, in that case, the tree is unordered. Otherwise, it will be ordered tree. So that should be quite clear in the context. All right? Okay, so this for now, we're going to say it's unordered. Okay, yeah. Basically, these are the two slides I put over here, right? That's ordered, and this one is unordered. Okay. All right, any question until here? Okay. Why don't we take another 10 to 15 minutes and then we'll take a break? Would that be okay? Okay. So let's talk a little bit about Java, and then we will be ready to actually go to the binary tree. For the Java one, let's now, first of all, explain about the structure of the code. And I want you to remember right away. Remember in your doubly linked node, right? Here we're talking about what a tree node is like. But for the doubly linked node, we got the previous reference and we got next reference. Now I want you to see analogy. I'll try to remember to connect with you, maybe after the end, at the end of this discussion. Think about if you want to apply some analogy from previous to the case of tree, what would it be like? What about next? What would it be like in the tree? There's some weak analogy you can make, but I'll talk about it later. Question? No, not now. You can think about it, and then we can walk over it. Yeah. All right, let's now take a look at the structure. And this will be very important for your assignments and programming tests. Let's be careful. Okay? And we're also doing a generic tree, generic parameters, right? You can see tree, and then with generic parameter E. So once E is instantiated, every occurrence of E is going to be instantiated accordingly, right? I'm just circling the E that you should really watch out for. E here, and also E here, and E here, all right? And what attributes do we have? We have the elements. Oh, this one is definitely should be there too. We got elements, we got parents, and we got children, which is an array of TreeNode. Okay, let's now visualize this right away. At excuse me, at a runtime, it's going to be an objects, something like this, and it's going to be TreeNode. And we have elements. That one there is going to point to some objects. Okay? Can be string, can be integer, can be person, can be bank account, whatever. And also we got parents. Parents would be, you can think about, is going to point to the node that's going to exist above. All right? And then what about children? It's a general tree, so it's going to be an array. That one there is going to be an array of nodes. Each one of them is going to be another tree node. That's the rough structure at the runtime. Okay? And over here, we simply we got an array, so we have to somehow maintain a counter for how many children we actually got. An array might be initialized to be of size 100. That doesn't really mean you got 100 children right away. So you have to use this NOC counter to know exactly how many children you actually got. Right? It's a very basic way of manipulating the array. Okay, NOC over here is about number of child nodes. Question?
Wouldn't it be better to use an array list here to get around the whole array resizing?
Yeah, but again, I think at this level, since we just starting to program about trees, so I think everything should be done from scratch. You're right. Beyond this course, by all means, you should really replace this by maybe some library structure, just make it easier. Sometimes it might make sense to even put a hash table, but anyway, that might be a little bit too much. Yes.
By children, you mean the immediate descendants of the characters.
Exactly.
Okay,
yes, just the next level. So you can think about here, the children, for example, here, from this node, what will be the children? The immediate below level. Okay. Okay, and then let's see. And we got a constructor. All right, guys, I can tell you that this is rather straightforward except for one line that's very confusing. Okay, I'll try my best to clarify to you. It's more at the level of the Java language, which can be very weird, but I will try to point it out to you. But that's something you will have to try too. Look at this line here. What this line tried to do, This children, like this array over here. We want to create an array of TreeNode, and somehow it's trying to do some casting. But the expression it is trying to cast into is using some weird expression over here. Okay, that's something I want to discuss separately, just to give you some warning, because you might need to use this during the programming test. You may need to. Okay, so I would say instantiating generic structures. And there's one page I would like you to maybe look it up, maybe after the class, but I'll just sketch that over here. If you remember, one of the class we declared before is called class array stack. Okay, it's definitely one class you will have to look into. Okay, just review. And then, if you remember, we actually got some private attributes called data. Okay, and then we have the constructor, public array stack. All right, and we had to write a line over here to instantiate the array. Right, that's something we covered earlier. Right, what we said before was you should really create an object array and then cast that into the generic type. Okay, let's do that. So it's going to be data. Yeah, my bad. You see, that's when you try to write the code. It could be very easy to make mistake. E type and then data. Okay, good. So data will be new. You would say object array of certain size. I'll say dot dot. It's not so important here. And then you have to make sure you cast the entire thing into the type, which would be this. Okay, this is something you would have seen already. When the generic type is directly the type of the array over here. But now, we're having something that's more complicated. Okay, I'll show it to you side by side. Now, what we have is, let me put on the right-hand side, and this is the class we are worrying about, the TreeNode. Okay, let me put it there. Let's say we have our class TreeNode, and then E, and then let me copy just the one you need. So private, okay. So that one has private TreeNode of E array. I'll say C, standing for children. Okay. And you want to compare right away. This and this over here, they looks very similar, but this one here has one level further about the structure. You can see E here, you can see E here, you see the array here, you see the array here. But in this case, we are trying to wrap around the E within the TreeNode. That's the extra complication we have. So Java asks you to do that slightly differently. Okay. The E is wrapped within the TreeNode. Okay. All right. And then let's see how we can instantiate this. Okay, we're going to say public, and then we got TreeNode. Let me show you what you might have been thinking, what you can write. By applying the same logic, we can say the children is simply, we want to cast into the TreeNode of E array. And then we can simply say new objects. This one here makes 100% sense. but it just wouldn't work in Java. If you do this, I encourage you to try. You're going to have class cast exception from Eclipse or any IDE you use. So you cannot do this, all right? Again, if the structure you're trying to instantiate has E directly, you can use this, no problem. On the other hand, if the structure you want to instantiate has not just E, but E is wrapped around within another generic class, then you cannot do that. What should you do? What you should do instead is like this. I'll write it down, okay, and then I'll leave the rest to you. This is what you should do. Okay, you still want to do a cast. Let's start with bits by bits. So you want to say C equals, you still want to do the cast. TreeNode E. The cast should still be there. But this part here is going to be a little bit different. You're basically going to turn this part over here into some method call from some Java library. So what you will do is you're going to say array.newInstance. Okay? Array.newInstance. And it will take two arguments. The first one, let me leave blank for now. The second one is going to be whatever this is. Okay? So dot, dot, dot. The size. Right? When you see the example code from the lecture slide, you will see exactly how this can be done. Okay? Now, what about this part over here? Okay? This part here is actually going to be some expression like this. We want to give the type of the array. And the type of the array that we want is actually a tree node of E. In this case, the tree node of E is exactly the current class. Agree? Okay? So that's why you can put just this .get class. Okay, so this is really referring to the tree node. This over here is really referring to the tree nodes over here. Okay? That's the correspondence you want to see. Okay? Alternatively, I believe you can also say something like this. Okay? I'm going to put over here. Alternatively, if somehow the current class is not the class you want, then apparently you cannot do this. What you can do is just put the class name verbatim. You can say tree nodes. Let me double check with this syntax, and then I'll confirm with you. But I believe this is what you can do. And then dot get class. Okay, this one here, let me put a big question mark. I'll double check this, and then I'll confirm with you on Wednesday. Right? But conceptually, what you want to know, when you try to do some initialization of the array where the generics is wrapped within another class, you cannot do just this. You cannot. All right? Because I don't want you to run into class cast exception in the programming test. Okay? Be careful. And for this one, I'll confirm with you on Wednesday. Okay? All right, guys, any questions? Yes. Mm-hmm. Yeah, this will be given, yes, indeed. So in the programming test 1, once you see the practice test 2, you actually see, okay? But I believe you will be given a tree node class, indeed, yes.
Oh, I was just talking about
this one here, right? Yeah, you'll be if the tree node class will be given to you, that line will be given to you as well. I wouldn't leave them blank and ask you to fill it in, not really. But I'm just saying, maybe as you are building your own algorithm, sometimes you might find a need to do something like this, in which case you have to know where to look up the syntax, right? All right, guys, why don't we take a very quick break, very short, and then take attendance. Oh, before that, question. You mean, okay, are you talking about the array over here?
Yeah, because the array can apply
Yeah, exactly. So yeah, you're right. So what we are talking about, at least for the practice in assignments and programming test, we're talking about order tree. Yes, yes. Yeah, your classmate made a good observation. Since array itself has the notion about ordering, it's a linear structure. So when you're programming for the assignments or for the test, yes, we're talking about order tree, indeed. All right. All right, why don't we let you have a short break, but before that, why don't we take attendance? Okay. All right, guys, you can just get your device ready, and then you can now check in. Okay. Yeah, anyone who has any issue, please come forward for the sign-up sheets. Everybody's good? Can I close it? All right, I'm going to close it. Thank you. Take a 2-minute break, and then we'll come back to talk about more stuff. Okay, take a 2-minute break. Of course. This one. Yeah. Yeah. Of the array. We're basically reproducing this line over here, but just by rather than just doing that directly by yourself, you're calling some library method to do it. Because I believe that's the reason. If you go to the array class and go to new instance method, I believe the definition is it's going to return an object array according to the API. So as far as the compilation is concerned, you cannot just assign this directly to C, which is of TreeNode array. So that's why you still have to do a cast. Yeah. Yes. You mean for the backup lecture?
What was the other one?
So say it again. I didn't quite catch you.
At the beginning of the first slide, I saw you had the like some announcements.
Yes. I believe they were about, one is programming test 1 result. It'll be released by Friday. And the other one is about the 2 makeup lectures you will need to study.
Okay.
Yeah, these are the 2 announcements.
Written test 2 will be based on, because for written test 1 we are doing Bigelow notation.
Yeah, that one is not going to be cumulative. So I will announce the precise coverage maybe by the end of today or early tomorrow.
Okay.
Yeah. All right, sounds good. All right, guys, 1 minute, please. Just 1 minute.
Actually, one more question. Could you go back to this slide? This slide right here.
This one?
The one after it. So is this also generally how we do how wrapper classes work in general, or is this just specific to trees?
This one, I would say this one here is more specific to generics, especially you want to have an array of generic classes rather than just an array of generic types. They're quite different, right? Because you see over here, this is an array of just E directly, where E is a generic type. But this one is an array of not just E directly, but a tree node of E. There's one extra layer of complication. For that one there, you just cannot use this one here. That one is going to give you a class cast exception. That's really a limitation for Java language at the moment, I would say. They didn't really do generics very well. But a workaround would be you have to use some help from the array library class.
We're casting the new instance.
we are creating that new instance by using this, by calling this library method, and then cast that into whatever type we like. All right. Okay, gotta be quick, otherwise I'm gonna resume. Okay. All right, guys, let's get started again, please. All right. Okay, so I would suggest we got about 25 minutes-ish. We definitely want to finish about the Java discussion about implementing general tree. Maybe that will be it for your written test number 2. I think for Wednesday, we're going to talk about more mathematical property of your binary tree. Okay, I think that could be the way to go. Let's see. Okay. Well, if we go back to the slides, what we discussed before the break was about this particular class, right? Of course, when you actually get to assignment number 3, you will definitely have to work with this class very closely. Okay. I forgot the exact detail, but I believe in your assignment number 3, the children over here, rather than an array, is going to be replaced by singly linked node. I believe that was the case, but we'll see. All right, so we got tree nodes and then different methods over here. Right, so these are rather straightforward. And what you really want to do is, if you go to the lecture site, right, you will see under, let me show to you. You can see generic general tree. If you go there, you will actually see the example code. You will see how we actually implemented the various methods. Okay, over here about set elements, add child, and etc. I want you to try one method over here yourself, how to remove a child at a particular index. That one there, if you want to remove something from an array, expensive, linear time, right? You should really get alarmed right away. But you should still know how to do it. All right, let's now try to trace some code to really get a very nice feel about implementing tree in Java. Well, I would say if you already feel comfortable about implementing singly linked lists in Java, this one is a very natural extension. Let's see. Okay, it's not too bad. Let's say this is what we want to achieve, first of all. We want to build a tree that goes like this. We want to have the parents, Agna, who has 2 children, Elsa and Anna. A very simple tree we want to build. Okay. How do we do that? Okay, let's go line by line. So we want to create 1, 2, 3. 3 nodes in total. Okay, and then let me just refer to my notes. Okay. All right, the first line here, we have the reference Agna. Okay. So it's going to be Agna, and it's going to point to some nodes of type TreeNode. Okay, just for better visualization, I'll put Tn over here. So you know it's a tree node. And it has 3 attributes. Let me remind you what they are. It has the elements, it has the parents, it has the children, right? 1, 2, and 3. So I'm going to divide them into 3 parts. All right, in the beginning, we simply got the parents being null. Okay, that's the parents. And also we got elements. And element is going to be a string. Right, you can see we passed the string type over here. That one there is going to be the name, Agna. All right, and then in the beginning, we are also going to, let me show to you how you can look at that. You can see we define the maximum number of children to be 10. And when we actually initialize the array, it's going to be 10. All right? So what we will do is we're going to create an array over here of size 10. Okay, so we got 0, 1, 2, all the way to 9. That's the object structure. All right? Again, it has 3 attributes. You have the parents, which is a single reference of TreeNode. You have the elements, which will be whatever data type you have. Also, you have the children, which is going to be an array of tree nodes. All right. What about the second node? Very similar. So I'm going to be a little bit lazy. I'm just going to copy this. And I'll make it a little bit smaller. Okay. Okay, this one here, let me change that to be purple. And this one over here, change that to be, how about this? Okay, I'll change the names as well. Okay, okay, let's see this. And the second one, we're going to create Elsa. So it's going to be Elsa. Elsa itself is also going to be, for the moment, no parents. And then the name is going to be Elsa, of course. Let me change that. And then also has an array of size 10. And currently, every element in the array simply point to null, right? And the final nodes that what I want to create is Anna, okay? So this one here is going to be Anna. And then, of course, the name over here is going to be Anna. And as you are studying for written test number 2 for next Monday, you may just want to compare this fragment of code over here with approach number 1. When we talk about how it can initialize a chain of nodes, we basically create each node in isolation. And then we try to set their next references accordingly. That's basically what we're doing here. All right? All right, let's now try to do this guy here, right? The first one. Let me say here. Okay, number 1, Agna the add child to be Elsa. That means you're going to have index 0, and this one here should be pointing to Elsa. This is step number 1. Well, I'm ignoring some detail about tracing exactly how the add child is going to work. That one is rather basic. You can take a look at the source code I made available to you. Take a look. If you need trouble, if you have trouble understanding it, let me know. All right, I'll trace that together with you. For now, I assume you might just be fine. The next one, Agna, again, the same node, add another child, Anna. So that means it's going to be now index 1, right? So this will be number 2. So it's going to be index 1, and that one will be pointing to Anna, number 2. Okay? And so far, we are building something that makes sense. We have a node which has 2 children. From the diagram, it seems like we are done. But as far as implementation is concerned, you're not done yet. The parent and child references should be symmetric, which means if you have Agna pointing to Elsa, you should also have Elsa pointing back to Agna. That's something you want to make sure you always do programmatically. Otherwise, you're going to have some trouble when you try to do recursion. Because when you do recursion on the tree, you may sometimes want to start with a node and then go downwards. Also, sometimes you may want to start with some nodes and go upwards. You never know which way you might want to go. You want to make sure both ways will work for you. All right? All right, so what we do is we're going to set the symmetric nodes. So the next one is going to be number 3 and number 4. Number 3 and number 4. Number 3, Elsa. So Elsa, the parents, which is going to be, rather than pointing to now, is now going to point to Agna. And number 4, so this will be number 3, right? Number 4, for Anna, the parents, rather than pointing to now, is now going to point to also Agna. This is number 4. Okay, are we fine with this? It's not too bad, right? Okay. Question? I see what you mean. You're basically saying, should it be part of the addChild method implementation there? It's going to set whoever this is, the parent, to be something at the same time. Yeah, it can work, but I'm just saying for our API, we want to do these two separately. Just make it explicit for you about what you should really do. Yeah. All right, so here we got some checks over here. Okay, so let's say egg.getParents. Egg.getParents should be still null, right? That's passing. Egg should be the same as Elsa.getParents. Egg is pointing to this object over here. Elsa over here, .getParents is going to be also the same objects. So that's why they have the same reference, right? It's something called aliasing. Right? You can also check about the length of the array. For example, here, you can see how many children do we have in the array? 1 and 2. Okay? It is really up to this particular NOC counter that's maintaining. So you really want to look into the source code and see how this is updated. Okay? And also we got, okay, let's see this. I'll give you guys something to think about. Okay, aliasing. For example, we might say egg.getChildren, which give you an array, and then I want to go to index 0. Okay? That one there is indeed Elsa. But I can also give you another one. Number 1, number 2, and also number 3. What about Elsa.get parents and then .get children? Right? So these three expressions over here, 1, 2, and 3, they all refer to the same objects. Right? Let's see. Elsa is referring to this object. That one is obvious. Egna.getChildren at index 0. Egna.getChildren at index 0, which is also pointing to this object. Right? What about this one here? Elsa.getParents. Elsa.getParents is going to give you this object over here. And then .getChildren at index 0 is again going to give you these objects. So they all refer to the same objects. So aliasing is also very important. In the test or in the exam, I might just give you different expression for you to choose which ones actually refer to the same objects. So you ought to know how to draw diagrams like this. Okay? All right, any question about this? Right, this one just about setting up the tree structure. And after this, I think you guys are already ready to really start doing assignment number 3. But to really help you a little bit more, let's now do some example. We got about 10 minutes. Let's see if we can do both. All right? Question? Sorry, say it again. Yeah, exactly. So here, Agna over here, when you say get children, it's going to return this children array. And that one there, if you go to index 0, that's going to give you the object over here. Yes. Yeah, if you look at the actual source code, you will see how the get children was implemented. It's actually quite straightforward. Mm-hmm. Yep, so whether you want to trace the code using this or you want to trace the code using this, I would say it's completely up to you. If you're able to answer aliasing question like this already just by using this, by all means, go for that. I'm a little bit worried that for some of you, this might seem a little bit too abstract. You cannot really see how the pointers actually work. So that's why I try to get down to the very much detail. So in the test or in the exam, in any scenario, I would say go with any tracing method you feel more comfortable, as long as it can help you answer questions and solve problems. Go ahead.
When you add a child, the array checks if it's a duplicate.
Sorry, say it again.
The array checks if it's a duplicate. It's going to have multiple children.
Yes, it's going to have multiple children, but the way it's going to work is like this. So let's say, for example, let's say I have already added, let's say, Elsa to be the child. Okay, so you can see Elsa at index 0 over here. Okay, let's say I want to add another child. In that case, I cannot simply replace index 0 by another pointer. That will overwrite the previous child. So what I want to do is I want to go to the index 1 and then assign its value to the tree node that I want it to become second child. Maybe that's what you're asking, or?
But if, let's say I'm adding Elsa twice, does it check to see if there's a duplicate?
Okay, good question. The question was, let's say after adding Elsa and Anna, let's say I want to add Elsa once more as a third node. No, currently it doesn't really check to see whether you got duplicates. No, it doesn't check. So the TreeNodes class I gave to you is a very general one. If you want any additional checks, you may want to do that elsewhere. Yeah. Okay. All right, let's now try to do at least one example, if not two. All right, the first one, how do we compute a node's depth? Right? We talked about the depth before the break, but only at a conceptual and visual level. How do we do it in Java? Okay. As I hinted to you, let me just say it again. Okay, and then I'll show you the code directly. Okay, because I really want to finish these two for today, so you can definitely get started with your written test 2 preparation. How do I calculate the depth of Vanessa? It's going to be, number 1, the edge. And then, number 2, recursively, what is the depth of Vanessa's parents, Elsa? So these are the two components you will see in the Java code. All right? So in the slides, you will actually see the base case. If the node you're given is already the root, in that case, the depth would just be, by definition, 0. Otherwise, you have to go up one level to see what the depth is for the parents, right? That's the recursive case, right? The code is incredibly simple. Let's now take a look together. And then we can do a little bit tracing. Okay. So the depth over here, right? So we got integer, depth is going to return integer, and we got tree nodes. So this can be some arbitrary node. Arbitrary node in the tree. And you can see the way I try to call the depth method here. I try to apply to David, Ernesto, Chris, Elsa, Anna, Shirley, Vanessa, Peter, right? Right? So any node in the tree. And you can calculate the depth. Okay? What we're saying is, if the n.getParents equals null, what does that mean? Yes, that means the node is the root. This one tells you, also you can see from the previous page, Agna parents is null, so the root. And by definition, the root, so the depth of the root is simply just 0. And what about if it's not a root? It could be here, it could be here, or it could be here. If it's not a root, you're going to say 1 plus the depth of n.getParents, which will be here. But we're going to do tracing together just for 1, so you will see what's going on. So let's trace this one together about the depth of Vanessa. And then I want you guys to also take a look at the source code and make sure you're comfortable, number 1, making such call, and number 2, see what the return values are. That's important. Okay, let's try to chase it. That might be what we can do today. And as for the height example, it's going to be very symmetric to what we're doing here. I'll leave that to you as a self-study. Very simple. Okay, let's just do this one properly. Let's say I want to calculate the depth of Vanessa. Vanessa.getParents is not equal to null, right? In that way, we have to, first of all, the edge, and then we want to calculate the depth of her parents, which will be Elsa. Okay, so what do we do? Let's unfold, which would be 1 plus the depth of LZ. Guys, this will be the very critical stat you want to make sure you can really follow, right? In order for me to calculate the depth of Vanessa, I'm trying to reduce the problem to be something smaller. I'm going to say it's going to be this edge over here plus the depth of its parents. This is a recursive call. It's a strictly smaller problem because I'm getting closer to the root. Okay? Strictly smaller problem because we are now getting closer to the root. All right? Now, how do we calculate the depth of alpha over here? Okay? Are we reaching the base case? Not really, because alpha that get parents is not equal to null. So we don't really do this just yet. It's going to be 1 plus whatever the parents of alpha is. So that means we're going to put this edge over here, and then we're going to calculate the depth of alpha's parents. Okay, let's write it down. So it's going to be, again, 1 plus, don't forget the 1 plus from before. And this one here is also going to be 1 plus. And the 1 plus is here, right? 1 here, and also 1 here. And then here we got the depth of quiz. Again, the problem has been reduced even smaller because we're getting even closer to the root. Okay, one more. Okay, don't forget the 1 plus here, and don't forget the 1 plus over here. And then, in order to do that, we're going to be calculating, because quiz is not a root just yet, so another 1 plus. And then, this will be David, right? So that one is going to be 1 plus the depth of David. And indeed, this will be the base case, because David that get parents is going to be, by definition, null, because David is the root. Okay? Base case. So this value over here is going to be 0. And if you do the math, it's going to be 1, 2, 3. Exactly the 1, 2, 3 edges we talk about. Right? It's the tracing of the recursion. Are we okay about calculating the depth? Okay. So what you should really review, I got 2 minutes. I think that will be the only thing I want to go over. You want to make sure you understand the base case and how to trace it, and also how to calculate for others. These are other examples. Maybe just take 1 minute, okay? Just help you a little bit when you study for the heights. This will be the code for calculating the heights. It's not too bad, slightly more complicated, slightly. The height is going to be, first of all, let's get all the children for the node. In order, let's say this. In order for me to calculate the heights, first of all, I need to get the children. Right? That's n that get children would do for me. And then, if I simply don't have any children, in that case, I'm basically talking about some external nodes. In that case, the height would just be 0 by definition. It's like the base case. Okay? Otherwise, I'm going to go over the children list 1 by 1. Go over Ernesto, go over quiz 1 by 1. And then for each one of them, I'm going to calculate the heights of their children. And this is where the recursion will go. Okay? Okay, this is where the recursion. Recursive calculation of the heights. And then you're going to find out the maximum. And then you got to return that. That's what you will do. All right, so for your written test number 2, it's going to cover until, let me tell you the slide number. It's going to cover until slide, okay, so that's unfolding. You can also take a look. Okay, until slide 22. Okay, I'll make it also precise when I release the guide to you. Right, so on Wednesday, we're going to continue with the tree with more mathematical property, but for your written test too, only up to slide 22. Thank you, and then I'll see you on Wednesday.